In the previous session, we studied about small signal half-wave rectifiers. Now in this session, we'll study about active filters. Before moving on, we should know what a filter is. So filter is an electronic circuit that is designed to pass only a desired band of frequencies and attenuate the undesired band of frequencies. So these filters can be classified as analog or digital, and in analog it can be passive filters or active filters, and it can also be classified as low pass filter, band pass filter, high pass filter, band reject filter, and this band reject filter is also known as band eliminate or band stop filter. So now we'll come to know about all these four filters in the upcoming session. So first of all, we should understand what a passive filter and active filter is. So passive filter are those filters that use passive components such as resistors, inductors, and capacitors. And what do we mean by an active filter? So active filters are those filters that make use of transistors or op-amps along with passive components like resistors, inductors, and capacitors. So active filters can further be branched out as first order filters, second order filters, and third order filters. So based on what will they classify? Based on the rate at which the output falls off at the edge of the frequency range. So if the fall off rate is 20 dB per decade, if the gain falls by 20 dB per decade of frequency, the filters are classified as first order filters. And if the fall off rate is 40 dB per decade, the filters are classified as second order filters. So we'll be studying about first order filters and second order filters as low pass filter and high pass filter. This third order filters, it's not there in your syllabus, but third order filters are those in which the fall off rate is 60 dB per decade. And the active filters are more advantageous than passive filters because they are more economical because of absence of inductors. Now what will these inductors do? These inductors will dissipate more power because they are more bulky. And one more disadvantage along with it is that it is more costly when compared to resistors and capacitors. So, and one more advantage is it is capable of fitting it any environment, meaning it is easier to tune or adjust any frequency when compared with that of passive filters. And in active filters, the source and the load have excellent isolation. This is one of the good advantage of active filters. And in active filters, op-amp can easily be controlled in the closed loop fashion. Hence, active filters input signal is not attenuated. So these are the advantages of active filters over the passive filters. And let's see what a low pass filter, high pass filter, band pass filter, and band reject filter means. So first let us consider low pass filter. Low pass filter, to talk in general terms, it should pass the low frequencies and it should attenuate the higher frequencies. So this is the characteristics curve of low pass filter. You can observe here the lower frequencies are passed and the higher frequencies are attenuated. So this, the graph indicated with the dotted line, is the ideal response, but practically you will not get the same graph, it will not decrease suddenly, it will decrease gradually in the practical case. So the frequencies which are passed, this particular band is called pass band, and for those frequencies which are attenuated, that band will be indicated by stop band. So we have written here, the dotted line represents the ideal response, the straight line represents the practical response. So here the particular frequency at which the gain starts deteriorating is called high cutoff frequency. So frequency band from 0 hertz to this higher cutoff frequency is called pass band, and for frequency greater than higher cutoff frequency, it is referred to as stop band, and the bandwidth is equal to higher cutoff frequency minus lower cutoff frequency, that is fh minus 0, that is equal to fh. And at this particular frequency fh, the gain is given by the corresponding value minus 3 dB. You have all performed experiments in analog circuits lab and you know about all these. You're going to just write whatever you have studied over there, and you're going to explain it in detail. And this is about lower cutoff frequency. Next we have low pass filter, and next we have high pass filter. So this is the characteristic curve for high pass filter. You can see lower frequencies are attenuated and the higher frequencies are passed by the filter. So the curve indicated by dotted lines is the ideal response, and the straight line indicates the practical response of the high pass filter. So the frequency range from FL onwards is referred to as pass band, and from 0 to FL, this is the stop band, because the frequencies in this region are attenuated. Okay, and next we have band pass filter. Band pass filter meaning it will pass only the selected band of frequencies. So let's say if I select frequencies from FL to FH to pass, and beyond FH and below FL I want to stop, so I will use band pass filter. So you can see here, frequencies from FL to FH are passed, and beyond FH and below FH they are attenuated. So the graph indicated by dotted lines is the ideal response. So this is almost this rectangle or square, you can see. This is the ideal response, and this curve represents the practical response. It does not increase simultaneously, it will increase gradually and decrease gradually. So next we have band reject filter. So whenever we want to reject a selected band of frequencies, say from FL to FH, I want to reject those frequencies, I will use band reject filter. So here you can see frequencies from FC to FL to FH are rejected, and frequencies below FL and beyond FH are passed. So here this region is called pass band. This also is called pass band because they are passed, and the frequencies in this range are attenuated. So this particular band is referred to as stop band. And the same, the dotted line characteristic curve represents the ideal response, and this curve represents the ideal response of the band reject filter. So this FC in both these cases, band pass and band reject filter, are called critical frequencies. That is nothing but the peak value here. and here also. And next we have a curve which represents the phase shift between input and output voltages for all pass filters. Meaning, if this particular frequency passes all the frequencies well, but the input and output voltages will have a phase shift of 5. One thing you must observe here is the amplitude of input voltage and output voltage is equal for all frequencies. So here this red signal is the input signal, and the one indicated with the blue is the output signal. You can see these two signals have phase difference or phase shift of 5, and you can observe that the amplitude of both the signals are same at all instants of time. And next we have study of first order low pass Butterworth filter, second order low pass Butterworth filter, and first order high pass Butterworth filter and second order high pass Butterworth filter. In this session, we'll study about first order low pass Butterworth filter. In the upcoming sessions, we'll come to know about the other three filters. So first, to start off with the first order low pass Butterworth filter, this is the configuration of low pass Butterworth filter. This is called first order because in the input side we are using one pair of resistor and capacitor, hence the name first order. And this is the frequency response curve for the first order low pass filter. It's the same as we have studied before. So the curve indicated by dotted line is the ideal characteristic curve, ideal frequency response of low pass Butterworth filter, and this curve indicated with the thick line is the practical response. And you can see that the roll off rate is minus 20 dB per decade, hence the name first order. From the graph also you can come to know that it is first order, and from the configuration of the circuit also by using by seeing one pair of R and C at the input side, you can identify that it is a first order low pass Butterworth filter. Now this circuit is a non-inverting configuration. As you can see here, the input signal Vin is given to the non-inverting terminal, and this potentiometer here, this potentiometer indicated by R, and this capacitor C at the input side is used for filtering purpose, and this resistor R1 and RF is used to provide the required gain for this op-amp 741 or 351. Okay, any value of gain can be obtained by selecting appropriate values for R1 and RF. Now, I already mentioned that since only one resistor and one capacitor are used at the input side, this is called first order low pass Butterworth filter. Now, see, now we are analyzing this circuit for low frequencies and higher frequencies. We'll come to know how the low frequencies are passed and how the high frequencies are attenuated by analyzing the circuit for low frequencies and high frequencies. So first, considering the operation of the circuit at low frequency. At low frequency, this capacitor, as you can see here, this capacitor will have a reactance which is very high. The formula for reactance is Xc equal to 1 by 2 pi Fc. Now, if this frequency is very low, this reactance will be very much high, isn't it? So, this capacitor is considered as open circuit. This capacitor is considered as open circuit. So whatever the signal V in is given, it appears at the output voltage V naught. So V naught is equal to V in. So see here, V naught is equal to V in, which implies the gain that is given by output voltage by input voltage. If these both are equal, the gain will be equal to 1. That is nothing but unity. So as you can see here, the gain AF, it is equal to 1, and since output voltage is equal to input voltage, it is passing all the lower frequencies and it is indicated by pass band. Now beyond this FH, meaning higher cutoff frequency, beyond this we refer to as higher frequencies. So what will happen at high frequencies? This capacitance, the reactance of the capacitor XC is equal to 1 by 2 pi FC, isn't it? If this F is very high, if it is very high, this reactance is very low, isn't it? So if this reactance is very low, some amount of this will not be a open circuit now. Some amount of current will flow here, and the output voltage is very much lesser than the input voltage. So it will gradually decrease at the rate of minus 20 dB per decade. So the frequencies are being attenuated here, and this band is represented by a stop band. So this is the operation of the first order low pass Butterworth filter. This is the logic of operation. And note, low frequencies will be passed and high frequencies will be attenuated by the low pass filter, hence the name low pass filter. Now we will analyze the circuit. Now we are going to apply voltage divider rule at the non-inverting terminal. So we are going to apply voltage divider rule here. Okay, and we are going to find the voltage V1. Now this V1 is equal to the reactance of the capacitor, that is minus JXC into the voltage across it is V in divided by the resistance in this loop is given by R minus JXC. So this V1 is given by V in into minus JXC by R minus JXC, where this minus J into XC can be written as, we know that XC is equal to 1 by 2 pi FC. This minus J can be written as 1 by J. So minus JXC is equal to 1 by J 2 pi FC. And upon substituting this minus JXC in this equation 1, we will get V1 is equal to V in by 1 plus 2 pi FRC. So now this is the voltage at the non-inverting terminal of the op amp. Now this voltage is considered as the input voltage, not this V in. The voltage available at the non-inverting terminal is considered as the input signal to the op amp. So output voltage will be given by the gain times the input voltage V1 at the non-inverting terminal. So V0 is equal to gain into V1. Gain is equal to 1 plus RF by R1 since it is non-inverting amplifier. So the output signal V0 is equal to 1 plus RF by R1 into V1. And we know that V1 is equal to V in by 1 plus J 2 pi FRC. So from this we are going to find V0 by V in. that is equal to the gain of the total circuit, meaning the gain of the filter. So this is given by AF by 1 plus J into F by FH, where V naught by V in is the gain of the filter, and AF is equal to 1 plus RF by R1, and this F is the frequency of the input signal, and this FH is the high cutoff frequency of the filter, and this is given by 1 by 2 pi RC. And from this equation we are going to find out this is the gain, right? From this equation we'll find out the magnitude of the gain and the phase angle for the low pass filter. The magnitude of gain is, this itself is the gain of the filter. So magnitude of this gain meaning magnitude, see here, magnitude of gain is equal to AF by, this magnitude is given by, this is the imaginary term we have here, A plus JB, you can consider it as. Magnitude of this is given by square root of A square plus B square. So A is 1 and B is F by FH. So square root of 1 plus F by FH whole square. This is the gain magnitude, and the phase angle is given by the polar form. This is the polar component, polar component of the imaginary term. So here phi is given by minus tan inverse of F by FH, where phi is the phase angle in degrees. Now considering this equation 4, we are going to analyze the operation of overall low pass filter. Now, so now if this F is lesser than the higher cutoff frequency from this equation, if it is very much less, this term will almost be equal to 0, and square root of 1 will just be 1. So this will be AF by 1. It is nothing but AF. And like that, if you substitute F is equal to FH, you will get the magnitude of the gain as equal to AF by root 2, because you will get 1 here, and square root of 1 plus 1 is root 2, AF by root 2, 1 by root 2 is 0.707 times AF. And when F is greater than the higher cutoff frequency, you will find that the gain magnitude is lesser than AF. And the filter design steps. This is very much important in the problem solving. So you must remember these. This is very important. So how a low pass filter is designed is given here. So there are 4 steps. In this first step is we are going to choose a value for high cutoff frequency FH. We know that FH is equal to 1 by 2 pi RC. Now we are going to choose a value for this particular frequency, that is cutoff frequency. Okay. Then next step is we are going to select the value of C such that it is lesser than or equal to 1 microfarad. So this is the second step. First step is we are going to select a value for higher cutoff frequency. Second step is we are going to select a value for capacitor which is lesser than or equal to 1 microfarad. Probably it would be 0.01 microfarad. Okay. Next, in step 3, we are going to calculate the value of R using this formula. R is equal to 1 by 2 pi FH into C. We have already known these formulas in the previous design. Here I'll show you. R, see here. This we know that see here, wait, FH is equal to 1 by 2 pi RC, isn't it? So R will be equal to 1 by 2 pi FH into C. From this equation itself, you can obtain the value of R. So we know FH and C. We have already chosen a value for FH and C in the step 1 and step 2. And in step 3, what we are going to do? We are going to compute the value of this resistor R. And the last step is we are going to select the value of the resistors that will give us the required value of gain. So what are they? RF and R1 are the resistors that are chosen in such a way that we obtain the needed value of the gain of the op amp. So we are going to select R1 and RF according to the desired passband gain AF using AF is equal to 1 plus RF by R1. So these are the steps. You must remember these steps while solving problems. And next the topic is frequency scaling. So in some applications we will have to change the cutoff frequency of a filter from a value fh to say fh dash. So in this condition, in such circumstances, what we are going to do is, first we are going to multiply the resistor R or C, this resistor that we are going to use at the input side. We are going to multiply this resistor or this capacitor with a ratio of original cutoff frequency to the new cutoff frequency. So we have a problem based on this. While solving problem, you will come to know what it exactly means, but I will tell in a brief. If we are changing the cutoff frequency from one value to another new value, this method is called frequency scaling. In some applications, uh, it might the filter might demand frequency scaling, so this particular method is used over there. So how is it accomplished? The resistor at the input side or the capacitor, not both, any one, either resistor or capacitor, is multiplied by the ratio of original cutoff frequency fh by the new cutoff frequency fh dash. So now we have a problem to solve wherein we are supposed to design a low pass filter at a cutoff frequency of 1 kilohertz with a pass band gain of 2. And in that sub question is using frequency scaling technique, convert 1 kilohertz frequency cutoff frequency of low pass filter to a cutoff frequency of 1.6 kilohertz. So what have they given here? They're saying that in a low pass filter, the cutoff frequency is 1 kilohertz initially and the passband gain is 2. So considering these two values, we are supposed to design a low pass filter first, and then we are supposed to use frequency scaling technique and convert the lower cutoff frequency from 1 kilohertz to 1.6 kilohertz. So we'll uh, come to know how we have done that. So first, here we are supposed to design. So we are going to follow the 4 design steps. So first one is we are going to select the higher cutoff frequency. So here we are not selecting because it is all, they have already given that fh is equal to 1 kilohertz. So I'll write the higher cutoff frequency is 1 kilohertz. And next we are supposed to decide the value of C. So we will take C as equal to 0.01 microfarad, and next we are supposed to compute the value of R from this equation, that is 1 by 2 pi fc. Okay, f is equal to 1 kilohertz and C is equal to 0.1 microfarad. So by substituting these two values, we will get R is equal to 15.9 kilo ohm. So instead of, this is not a standard value, so we will use a 20 kilo ohm potentiometer and set it to 15.9 kilo ohm. Okay, and then in the last step, that is the fourth step, we are supposed to calculate the value of R1 and RF. So it is given that the passband gain is equal to 2. So since it is a non-inverting configuration, the gain is given by 1 plus RF by R1. So if this has to be 2, we have already 1 in this term of the gain, passband gain. So this RF by R1 should also be equal to 1 for AF to be equal to 2. So if this ratio RF by R1 must be equal to 1, R1 should be equal to RF. So R1 is equal to RF. We will choose uh, to for it to be equal to 10 kilo ohm. Now we have computed all the values, that is FH and the capacitor at the input side 0.01 microfarad and the resistor at the input side, that is 15.9 kilo ohm, and the two resistors that will decide the gain of the op amp, RF, R1 and RF, that also is computed here. So we know all the values. So you are supposed to draw the circuit diagram for low pass filter and indicate the appropriate value against those components R1, RF, C and this R. And you are supposed to plot a frequency curve for this low pass filter also. And next, this is the design part. Next, this part we have not yet solved this part of the question. So next we are supposed to use frequency scaling technique and convert the cutoff frequency from 1 kilohertz to 1.6 kilohertz, isn't it? So this frequency scaling technique, what we are going to do, we are going to multiply this capacitor or this resistor by the ratio of original cutoff frequency by the new cutoff frequency. So we will select the resistor to multiply by this ratio. FH is the original cutoff frequency and the new cutoff frequency is FH dash CA. FH is equal to, we are supposed to convert from 1 kilohertz to 1.6 kilohertz. So FH is equal to 1 kilohertz and FH dash is equal to 1.6 kilohertz, and this ratio is 0.625. We are not supposed to multiply both these values with this ratio. We are supposed to choose any one. We have chosen this resistor R equal to 15.9 kilo ohm to multiply. So I'm going to multiply 15.9 kilo ohm with this ratio. So I'll get a new resistor value R that I'm supposed to use in this place. In this place, in order to change the cutoff frequency to 1.6 kilo ohm. So here what is the new R value that I have got after multiplying is 9.94 kilo ohm, isn't it? So at the input side, we must use 9.94 kilo ohm in order to get a cutoff frequency as 1.6 kilohertz. So instead of 9.94 kilo ohm, when using the standard value, that is 10 kilo ohm, in order to get a new cutoff frequency is equal to 1.6 kilo ohm. So this is just a verification that we have done to check whether if we are getting 1.6 kilohertz itself as the new cutoff frequency. So cutoff frequency is given by 1 by 2 pi RC. Now we find out that R is equal to 10 kilo ohm by multiplying the initial resistance value, that is 15.9 kilo ohm, by the ratio of old original cutoff frequency by new cutoff frequency. We found that new resistor value is 10 kilo ohm. So by using this 10 kilo ohm, I will verify if I'm getting FH dash is equal to 1.6 kilohertz. So I will substitute R is equal to 10 kilo ohm and C is equal to 0.01 microfarad itself, and we have got FH dash is equal to 1.6 kilohertz, which means this resistance of 10 kilo ohm is correct. Whatever we have found out is correct. So This is about first order low pass Butterworth filter, and in the next session we'll study about high pass first order Butterworth filter.